Modeling with exponential functions. First, let's look at exponential growth from the perspective of doubling time. If the initial size of a population is n naught and the doubling time is a, then the size of the population at time t is n of t equals n naught times 2 to the t divided by a. So a and t are measured in the same units of time. So basically that could be minutes, hours, days, years, etc. But we have to make sure that those are measured in the same units of time. So this is a way of coming up with a population growth model if you know how long it takes for a population to double. So for example, under ideal conditions, a certain bacteria population doubles every 3 hours. Initially, there are 1,000 bacteria in a colony. In part A, we want to find a model for the bacteria population after t hours. So we know that n of t is equal to n naught times 2 to the t divided by a. And in this problem, n naught is 1,000 bacteria, and a, the time to double, is 3 hours. So the population model is going to be 1,000 times 2 to the power t over 3. And one thing to really be careful of here is you don't want to multiply 1,000 times 2 because this 2 is raised to a power here. So if that is a problem for you, one thing you could do here to kind of help remind you of that is you could put parentheses around this part. In part B, how many bacteria are in the colony after 15 hours? So for this, we simply need to find the number of bacteria when t equals 15. This will be 1,000 times 2 to the 15 divided by 3. And this is 1,000 times 2 to the 5th power, which is 1,000 times 32, which equals 32,000. And in part C, after how many hours will the bacteria count reach 100,000? So we want the number of bacteria to be 100,000. We're going to plug 100,000 into our model, which is right here. And if we do that, we get 100,000 is equal to 1,000 times 2 to the t divided by 3. And now we're just solving an exponential equation. So first thing I'll do here is divide by 1,000. These are going to cancel out, and 100,000 divided by 1,000 is 100. So this gives us 100 equals 2 to the t divided by 3. Now to solve this exponential equation, I'm just going to take the natural log of the left side and the natural log of the right side. After that, the power here can be brought down using properties of logarithms. So we have t over 3 times the natural log of 2. And then we'll multiply both sides by 3. This will cancel out the 3 here. And we'll divide both sides by the natural log of 2. And that will cancel out this. And that isolates t. And so t is going to be 3 natural log of 100 divided by the natural log of 2. And the last thing we'll do is plug this into a calculator for a decimal approximation. And we can see that we get approximately 19.9, or you could just round this to 20 hours. In the next example, a certain breed of rabbit was introduced onto a small island 8 months ago. The current rabbit population on the island is estimated to be 4,100 and doubling every 3 months. So what we have now is, what was the initial size of the rabbit population? So what we know is the number of rabbits in the population is equal to n naught multiplied by 2 to the t divided by a. In this case, a is equal to 3 months. That's the time to double. But we do not know what N naught is, right? We don't know the initial population. However, we do know the population after 8 months, so N of 8 is equal to 4,100. So what we can do is we can plug in 4,100 for N of t, and then N naught we don't know, and then we have 2 to the power, and then t is 8 because the 4,100 happens after 8 months, and then divided by 3, which was the doubling time. So now we just need to solve for N naught. So to do this, we could simply divide both sides by 2 to the 8/3 power. And this is going to give us 4,100 divided by 2 to the 8/3 is equal to N naught. And we'll just go ahead and plug that into a calculator. And this tells us the initial population was approximately 646. So next, for part B, estimate the population 1 year after the rabbits were introduced. So now we know the model is N of t is equal to 646 multiplied by 2 to the t divided by 3 power. So the number of rabbits after 1 year, okay, so we got to change that into months, and of course that's 12 months. This is going to be 646 times 2 to the 12 divided by 3. And this is 646 times 2 to the 4th power, which is 646 times 16. And of course, this is pretty simple to do on a calculator. We get here 10,336 rabbits. And finally, in part C, it says to sketch a graph of the rabbit population. So if you take N of t is equal to 646 times 2 to the t divided by 3, you can graph this using a graphing calculator, and you'll see exponential growth. And what you can see here is that we have a very rapidly growing population. Right, so we have the initial amount, which is about 646, and you can see after the first, second, and third months, it's growing relatively slowly, but as more and more time goes by, it begins to grow exponentially, and it grows really, really rapidly. Another way to discuss exponential growth is to talk about the relative growth rate. So a population that experiences exponential growth increases according to the model N of t equals N naught multiplied by e to the r times t power, where r is the relative growth rate. So this is a percentage growth rate per some unit of time. And t, of course, is time, and N naught is the initial population size. So if you're given information about the relative growth rate, r, instead of the time to double, this is the model that you should be using. Now, I do want to point out that when we talked about exponential growth for continuously compounded interest, we had a equals p e to the rt. I want you to understand that this formula here is exactly the same formula. It's just that we're renaming A to be N of t, that's the number in the population at some time t, and N naught is the initial number in the population. So it's the number when time equals 0. And then e to the rt, you can see, is exactly the same. So this formula is exactly the same as the continuously compounded interest formula. And in fact, if it helps you, you don't have to memorize it in this way. You can simply use this formula here. So for the next example, the initial bacterium count in a culture is 500. So we know N naught is equal to 500. A biologist later makes a sample count of bacteria in the culture and finds that the relative growth rate is 40% per hour. So R is going to be 40%, which is 0.4, and that's per hour. So for part A, we want to find a function that models the number of bacteria after t hours. So this is simply N of t equals n naught times e to the RT. So we're going to have n of t is equal to 500 times e to the 0.4 times t. For part B, what is the estimated count after 10 hours? So what is the number of bacteria when t equals 10? This will be 500 times e to the 0.4 times 10. And we'll just go ahead and plug that into a calculator. And this gives us an approximate value of 27,299 bacteria. So after only 10 hours, we have a lot of bacteria. Now for part C, after how many hours, so we're solving for t here, will the bacteria reach a count of 80,000? So now we have 80,000 will be the number in the future is equal to 500 times e to the 0.4 times t. So now we just solve for t by first dividing both sides by 500. These cancel out and we're going to end up getting e to the 0.4 t is equal to 160. And then we can take a natural log of both sides. That's going to cancel this out here, and we get 0.4t is equal to the natural log of 160. And so t will be natural log of 160 divided by 0.4. And this gives us approximately 12.7. And this will be hours, because time is measured in hours in this example. And finally, we just want to sketch a graph of this function. So you can see in the graph here, we have our initial bacteria, which is 500, and it increases very rapidly. Next, we want to compare different rates of population growth. So in 2000, the population of the world was 6.1 billion people, and the relative rate of growth was 1.4% per year. It is claimed that a rate of 1% per year would make a significant difference in the total population in just a few decades. Test this claim by estimating the population of the world in the year 2050 using a relative rate of growth of 1.4% and then also 1.0%. And then let's graph the population functions, both of these, for the next 100 years. So first of all, for the 1.4% growth rate, the population n of t is going to be 6.1, and that's billion, times e to the 0.014 times t. And for the 1.0% growth rate, the number in the population will be 6.1 times e to the 0.01 times t. So now to estimate the population in 2050, t is going to be equal to 50, because 2050 is 50 years from the year 2000, which was when the population was 6.1 billion. So 2000 is like our starting point of time. So the number in the population here after 50 years will be 6.1 times e to the 0.014 times 50. And we'll go ahead and plug this into a calculator in just a minute. And the number in the population here is going to be 6.1 times e to the 0.01 times 50. And we'll approximate that here. So as you can see here, for this population growth model, we're going to have 12.3 billion people in the year 2050. And in this population model, we're going to have 10.1 billion people in the year 2050. So let's remember, we began with 6.1 billion. So you can see that at this growth rate, in 50 years, the population will have more than doubled. And at this growth rate, in 50 years, the population will have almost doubled. So is this significant? Yes, it is, right? I mean, this is a huge increase in the number of people in the world. So either one of these growth rates is going to give a lot more people in 50 years. However, you can see that even just a small increase, so this growth rate is just 0.4% larger than this growth rate, gives you significantly more people in 50 years. So now let's just go ahead and graph both of these. And as you can see, they both start here at 6.1 billion. The 1% growth rate gives you an increasing exponential function. And the 1.4% growth rate also gives you an increasing exponential function. But you can see because basically the base of this exponential function is greater because of the greater growth rate. So we have a steeper exponential function here. So they are both going to result in a drastic increase in the population. However, the growth rate itself is extremely important because you can see as more time goes by, the difference between these two amounts becomes more and more profound. So in our next example here, we have a culture starts with 10,000 bacteria and the number doubles every 40 minutes. We want to find a function in this format that models the number of bacteria after T hours, and then we want to find a function in this format that models the number of bacteria. So if you recall, we have two different ways to model population growth. One is N of T is equal to N naught times 2 to the T divided by A. So this is the one that we use when we're given information about how long it takes to double. And then we have N of T is equal to N naught times E to the RT. And this one uses information about the relative growth rate. So let's start with part A here. We know that N naught is equal to 10,000. And we know that the time that it takes to double is 40 minutes. So the number in the population here will be modeled by 10,000 times 2 to the T divided by 40. And this is the model. For the other model, we have to figure out what the growth rate would be. And to do this, we can use the fact that the population doubles in 40 minutes. So when T equals 40, the initial 10,000 bacteria will become 20,000 bacteria. So we know the number at 40 will be 20,000. So I'm going to plug that in for N of T here. So 20,000 is equal to N naught, which is 10,000, E to the R times T, and T is 40 when this happens. So now to solve this, we'll divide both sides by 10,000. And this gives us 2 is equal to E to the 40R. Taking the natural log of both sides, natural log of E will cancel out here, and we have the natural log of 2 is equal to 40 times R. Finally, dividing by 40, we have R is equal to the natural log of 2 over 40. And let's plug this into a calculator to get an approximation. And we can see that this gives us approximately 0.0173. So our model here will be N of T is equal to 10,000 times E to the power R times T, and R is this value. So 0.0173 times T. Now what should be understood about both of these models is these are the same. They are modeling the exact same situation, so these two functions must be identical. So what that really means is 2 to the power T divided by 40 is the same as E to the 0.0173 times T. So these values are precisely the same as each other. And then I'll sketch a graph of both of these. And if you do this on a graphing calculator, if you sketch the graph of each one of these, you will see that they have the same graph. And as you can see here, the initial population is 10,000, and it is growing at an exponential rate. Next, we have radioactive decay. So if m naught is the initial mass of a radioactive substance with a half-life h, then the mass remaining at time t is modeled by the function m naught e to the negative r times t, where r is equal to the natural log of 2 divided by h. And again, h is the half-life. Now let's talk briefly about half-life. The half-life of a substance is the amount of time that it takes for half of the substance to decay. So if you start with, say, 10 pounds of a particular substance and you throw it into a field, the half-life would be the amount of time for that 10 pounds to become 5 pounds. Let's go ahead and take a look at the following example. So here we have polonium-210, and this substance has a half-life of 140 days. Suppose a sample of this substance has a mass of 300 milligrams. Find a function m of t equals m naught times 2 to the negative t divided by h, and then also find a function m of t equals m naught times e to the negative rt. So just like in the previous example, there are two different ways we can model this half-life, but what we need to do is find out what r is, right? So r is going to be the natural log of 2 divided by the half-life, which is 140 days. And so we're just going to plug this in on a calculator to get an approximation here. And you can see that we get a value that is approximately 0.00495. And I'm going to keep all of those decimal places here. All right, so if I want to model it as part A says to do, we're going to have m of t is equal to m naught, which is 300 milligrams, multiplied by 2 to the negative t divided by the half-life, which is 140. In part B, we can model it by saying m of t is equal to 300 multiplied by e to the negative r times t, where r is this value. So that's negative 0.00495 times t. And then we want to find the mass remaining after 1 year. So the mass remaining after 1 year, keep in mind that the half-life is 140 days. So 1 year is going to be 365 days. I can use either one of these. I think I'll just use the first one. So we have 300 times 2 to the negative 365 divided by 140. And let's go ahead and plug that into a calculator. And you can see that we get approximately 49.2. So we're going to say this is approximately 49, and this will be milligrams. So we'll have 49 milligrams remaining after 1 year. And this should make sense because we started with 300 milligrams. So every 140 days, this is going to be reduced by half. So this sounds about right. For part D, how long will it take for the sample to decay to a mass of 200 milligrams? So now we're going to let m of t equal 200. And again, I could use either one of these formulas. For this one, I'll use the second formula here. So we have 200 is equal to 300 times e to the negative 0.00495 times t. And then let's divide both sides by 300. On the left-hand side, we'll just have 2/3. And on the right-hand side, we'll have e to the power negative 0.00495 t. Let's take the natural log of both sides. This cancels out here. And we end up with the natural log of 2/3 is equal to negative 0.00495 times t. And then we divide both sides by this number. And again, plug this into a calculator. And this tells us it's going to take about 82 days for the mass to decay to 200 milligrams. And for the last part, we just want to graph this function. And you can see here that we start with a mass of 300 milligrams, and as time goes by, the mass is decaying. It's decreasing according to our function. In our final example, we look at Newton's law of cooling. If D naught is the initial temperature difference between an object and its surroundings, and if its surroundings have temperature Ts, then the temperature of the object at time t is modeled by the function T of t is equal to Ts plus D naught times e to the negative k times t, where k is a positive constant that depends on the type of object. So imagine you put something that is very hot or very cold in a room. After a certain amount of time, the temperature of that object is either going to heat up or cool down to the temperature of its surroundings. But the time that it takes for that to happen depends on what the substance is. Some substances hold their heat much better and much longer than other substances. And so this value K depends on the type of object. Let's take a look at an example. So a cup of coffee has a temperature of 200 degrees Fahrenheit and is placed in a room that has a temperature of 70 degrees Fahrenheit. After 10 minutes, the temperature of the coffee is 150 degrees Fahrenheit. So after 10 minutes, the temperature has cooled down from 200 to 150. We want to find a function that models the temperature of the coffee at time t. So first, let's go through and state what we know. The temperature of the surroundings is the temperature of the room, which is 70 degrees Fahrenheit. D naught is the difference between the temperature of the object and the temperature of the room. So that is 200 degrees Fahrenheit minus 70 degrees Fahrenheit, which is 130 degrees Fahrenheit. So we know that T of t will be 70 plus 130 times e to the negative k times t. Now we need to determine the value of k. What we know is that after 10 minutes, so when little t equals 10, the temperature of the coffee will be 150. So we know that 150 is equal to 70 plus 130 e to the negative 10 times k. Subtracting 70 from both sides, we have 80 is equal to 130 e to the negative 10k. Dividing both sides by 130 gives us 80 over 130 equals e to the negative 10k. Then I'm going to take the natural log of the left side, and let's realize that 80 over 130 is 8/13. And we'll take the natural log of the right side. And of course, over here, this cancels out. And we have the natural log of 8/13 is equal to negative 10 times k. And so k will be negative 1/10 natural log of 8/13. Now let's plug that into a calculator to get an approximation. And this gives us an approximate value of 0.049. So now we can model this thing by saying T of t is 70 plus 130 times e to the negative 0.049 times t. So I'm just taking this value and I'm plugging it back into here. So this is the answer to part A. Now for part B, find the temperature after 15 minutes. We just have to plug in little t equals 15. So this gives us 70 plus 130 e to the negative 0.049 times 15. And once again, let's plug this into a calculator. And we can see here that we get a value of approximately 132 degrees Fahrenheit. So after 15 minutes, it has cooled down to this temperature. In part C, after how long will the coffee have cooled to 100 degrees? So for this, we're going to let capital T equal 100 here. So this will give us 100 is equal to 70 plus 130 e to the negative 0.049 times t. And then we're solving for t, so we're going to subtract 70 here, which gives us 30. And then we're going to divide by 130. So we'll have 30 divided by 130 equals e to the negative 0.049t. Taking the natural log and reducing that fraction there, we're going to end up getting this, and these steps are exactly the same as what we did up here. And finally here we have t is equal to natural log of 3/13 divided by negative 0.049. And let's plug that in. And we can see that this gives us approximately 30 minutes. So it will take approximately 30 minutes for the temperature of the coffee to cool to 100 degrees. And finally, let's go ahead and do the graph here on a graphing calculator. And what I want you to see is, of course, the initial temperature is 200, and as time goes by, the temperature is coming down. But the asymptote is at 70, and this is because the temperature of the coffee cup can never go cooler than 70 degrees, because this is the temperature of the room that the cup is sitting in. So the temperature of the coffee is going to cool down and approach the temperature of the room, which is this horizontal asymptote here. And that concludes this video lesson.